A number of models are used for description of activity coefficients in fluid phase equilibria. Amongst the most commonly used equations are those of Margulis. Max Margulis was born in 1856 in Austria. The von Laer equation. Johannes Jacobus von Laer was born in 1860 in The Hague. He was a professor at the University of Amsterdam and a contemporary of Jacobus von 't Hoff and Johannes Diederik van der Waals, both Nobel Prize winners. The Wilson equation. Grant McDonald Wilson was born in Mexico and then moved to Oregon in the United States. And John Michael Prausnitz, who was the architect of the NRTL model for fluid phase equilibrium, NRTL standing for non-random two-liquid models. He is also the architect of the UNIQUAC model for activity coefficients, along with Abrams, and he was also involved in the UNIFAC group contribution method for estimation of activity coefficients in fluid phase equilibrium. My talk today focuses on activity coefficients not in fluid phases, but in adsorbed phase within microporous materials, and I will focus on the Wilson model for activity coefficients in the adsorbed phase and discuss how the commonly used Wilson model for binary fluid phase equilibrium, that is written here, can be extended to describe adsorbed phase equilibrium. In bulk fluid mixtures, the activity coefficients depend on the mixture compositions, say mole fractions xi. The situation is different for activity coefficients in the adsorbed phase within microporous materials. In this case, the activity coefficients of any component I depend not only on the adsorbed phase mole fraction xi, but also on the pore occupancy. We must satisfy two sets of limiting conditions. As the adsorbed phase mole fractions of any component I tends to unity, the activity coefficient of that component must tend to unity. Additionally, if the pore occupancy theta, which is related to the surface potential phi by this expression where Q sat mixture is the saturation capacity of the mixture, this expression for the pore occupancy, as this tends to 0, the activity coefficients for all guest molecules must tend to unity. CO2 capture with NaX zeolite is subject to strong thermodynamic non-idealities. These non-idealities stem from a non-homogeneous distribution of guest adsorbates, for example CO2 and methane, within the pore landscape of NaX zeolite. The CO2 tends to congregate near the extra framework sodium cations, and the inhomogeneous distribution of guest adsorbates within the pore structure of NaX zeolite leads to significant deviations from the behavior anticipated by the ideal adsorbed solution theory. Watch also my previous presentations, CO2 capture from ternary mixtures with NaX zeolite, segregation and congregation effects in CO2 capture with NaX zeolite on my YouTube channel. The theoretical background is described in detail in my earlier papers listed here. Let us see how the non-ideality effects can be captured with the Wilson model appropriately extended to describe mixture adsorption equilibrium in microporous crystalline materials. Let's start by examining adsorption of binary mixtures of CO2 and methane in NaX zeolite at a temperature of 300 degree Kelvin. The plotted symbols here are configurational-Bias Monte Carlo simulations for 50-50 mixtures in which the total fugacity in the bulk fluid phase is varied from low values of about 1 Pascal to post-saturation conditions that is achieved at about 10 megapascals. The green symbols are CBMC simulations for 50-50 mixtures of CO2 and methane. The blue triangles are CBMC simulations for 2080 mixtures of CO2 and methane. The inverted pink triangles of 1090 mixtures, and the red circles are for 595 mixtures. In all four cases, the excess free energy of adsorption, G excess divided by RT, which is defined as x1 times log gamma 1 plus x2 times log of the activity coefficient of component 2. This can be determined from CBMC simulations. This is plotted against the surface potential that serves as a proxy for the pore occupancy. We note that as the surface potential reduces to 0, the Gibbs excess free energy tends to 0. And therefore, an important requirement of the model to describe activity coefficients in the adsorbed fluid phase mixture is that as phi tends to 0, the pore occupancy tends to 0, and activity coefficients of both components tend to unity, and the Gibbs excess free energy also tends to 0. The satisfaction of this constraint requires us to extend the Wilson model for fluid phase equilibrium by introducing a correction factor denoted here, 1 minus exponent of minus c C is a constant times the surface potential phi. This correction factor is a proxy for the pore occupancy. And this ensures that as the pore occupancy reduces to 0, ln gamma 1 reduces to 0 and gamma 1 tends to unity. So the first important conclusion we draw is that for description of mixture adsorption equilibrium in microporous materials, we need to introduce the appropriate factor to correct for the influence of pore occupancies. Let's look at non-idealities for CO2 propane mixture adsorption in NaX zeolite. CBMC simulations for a bulk fugacity of 1 megapascals and varying compositions of CO2 in the bulk fluid phase are shown by the blue triangles, and the excess Gibbs free energy is plotted as a function of mole fraction in the adsorbed phase X1. We note that at either ends of the composition scale, X1 is 0 or X2 is unity and X1 is unity or X2 is 0. The activity coefficients of propane and carbon dioxide tend to unity, and therefore the excess Gibbs free energy reduces to 0 at either ends of the composition scale. So we need to ensure the satisfaction of this limiting case that is automatically obeyed by the Wilson model. So the message emerging from this video presentation is that the classic Wilson model for fluid phase equilibrium needs to be extended with an additional parameter in order to describe the influence of pore occupancy on the activity coefficients.